this is the outline. So first, let me give a brief introduction about this nanoglass. So what is nanoglass? Because our audience is from the different background, so I'm just afraid not all of you know this concept. So first, I just introduce a well-known concept. This is the nanocrystalline materials. And this concept is like this. If people can just reduce this grain size down to the nanometers, then a lot of atoms were located at the interface. Because these atoms located at the interface has a different atomic structures compared with atoms in the grains. So it will change the properties of the materials. This concept is proposed by the Professor Gleiter in 1980s, and this is really create a new research field in the material science. And generally speaking, just by reducing the grain size, and people can generate materials with new properties. For example, it can bring this plasticity in the nanocrystalline ceramics. And also it can bring such super plasticity, extensibility in the nanocrystalline copper. So if we just replace this crystalline grain into amorphous grain, then we will got this nanoglassy materials, or we call it nanoglasses. And just by introducing this glass-glass interface structures, these atomic structures and all the structure-dependent properties of the nanoglass may be controlled. And this is a really breakthrough in the amorphous materials, especially in the material glass, because today most of the material glass are prepared by this liquid quench. So the atomic structure of this material glass is hardly modified by design. And the interface in the nanocrystalline is easily to identify because in the grain there is an order structure. However, in the amorphous material, this is all a disorder structure. So how to identify the interface become a really questions. All people would ask, are interface possible between amorphous grains? So if the answer is yes, so how about these structures of the interface? How about these compositions? And the most important is what's the consequence for the properties? All these fundamental questions are our interest. So we just surrounding with the interface structure in the nanoglass. We study the preparation, its structure characterization, and its evolution, as well as the properties of the nanoglass. So the first challenge for us is how to prepare this high quality nanoglasses. The traditional preparing method for the nanoglass is so-called the IGC. IGC means the inert gas condensation. So the principle is like that. So we can just evaporate this alloy in a high vacuum system filled with inert gas. And this evaporated atoms clouded with this inert gas and condensed into this amorphous nanograin size. And this powder, we can collect it and in situ compact it into bulk materials. So in our lab, we already set up a state-of-the-art IGC systems. And based on these systems, we can prepare high purity nanoglass without oxygen inside, and it's fully dense and bulk materials. And the second way to prepare the nanoglass thin films is this magnetron sputtering technique. So by control this gas pressure and this power and also the deposition mode, and we can prepare different nanostructured amorphous films. So like this coron structure, or this bamboo-like structure, or this random packing structure nanoglass. And recently we developed a new technique to produce this nanoglass, and this is called multi-phase pulsed electron deposition. So this technique, compared with IGC and sputtering technique, it looks like more suitable for the real application because the electron deposition don't need this expensive high vacuum systems. And also, he has the capability to produce large area materials. And this pulsed electron deposition actually already used to prepare the nanocrystalline materials for many years. But if we want to prepare this nanoglass, then the key is to using this multi-phase. That means you need to change this deposition current and duration to control this amorphous cluster nucleation and growth. So this technique detail, if you're interested, you can refer this paper on this material research letters, and we also apply to patents on this technique. And we did a lot of structural characterization on this electron deposited nickel phosphor nanoglass. And this is XRD, and this is high resolution TEM. And from this result, we can see this material are well amorphous structures. And the FM show a traditional this nanoglass feature from the surface. This is the nano grain structures. And from the XPS, we can see its high purity and without oxidation. And please keep in mind, this clean surface is very important to understanding this nature of the nanoglass. And we also using this small angle and wide angle X-ray scattering technique to get the statistical information of this bulk materials. And from this SAX data, and we can get the information about this particle size distribution in the nickel phosphor nanoglass, and which is around 12 nanometers. And from this wax data, and we can clearly see the red one is a nanoglass, and the blue one is a metallic glass. So we can see the difference from this SQ data, which indicate the nanoglass and the metallic glass has different atomic structures. So if we using this difference SQ from the metallic glass and the nanoglass, then we transfer to the real space, then we will find this coordination share is shift to the higher distance, which indicates there is a loser phase with a different short range order and middle range order in the nanoglass. And more obviously evidence we can obtain from this high resolution TM. And this is the image from the nanoglass. It's clearly to see this nanoglass consists of this green structure and the interface. And please notice all the region from the green and interface are amorphous. And there is no obviously chemical segregation from the APT measurement. And if you compare with the structure of the metallic glass, and you found its more uniform structures. And using this electron deposition technique, we can also tailoring the atomic structures, and just by using the different deposition rate. And this actually provides more opportunity to us to modify the atomic structure of the metallic glass. And this atomic structure also will be modified by this post-heat treatment. And we using this synchrotron X-ray diffraction technique, we can perform this simultaneous sex and wax study to investigate this structural evolution upon heating. And we first reported this polyamorphous phase transformation in the nanoglass. And you can see from this curve above a critical temperature Ts, and this sex intensity, this one decrease. And meanwhile, this wax intensity increase upon heating. So this indicates there is a solidification-like behavior happen. What does this mean? This means this low density interface structure transform to the high density core structures. So with reduced heterogeneity at these temperatures. And we can also got the similar information from the reduced pair distribution functions. And the nanoglass show a anomalous contraction. What does this mean? And this red one is the third peak position with upon heating, and it's just a shift to the short distance. That means the contraction upon heating. And while this metal glass just shows this thermal expansion upon heating. So this is also indicates there is a solidification-like behavior in the nanoglass. So we just described we can got the different atomic structure in the nanoglass, and we also can modify these atomic structures. So one would expect it there is some different property or unique properties in the nanoglass. So here we just show you some examples. First, we will show you this nanoglass has enhanced thermal stabilities. And this is the in situ X-ray diffraction pattern. And there shows this crystalline temperature of the nanoglass is much higher than this metal glass with the same chemical composition. And this indicates this nanoglass has higher thermal stability. And that indicates during this atomic rearrangement process upon heating, and the nanoglass with more free volume can reach a more stable energy state. And this is the thermal expansion experiment. And from here, we can see this blue one is a metal glass that show a linear expansions. However, the red dot line is from the nanoglass, and it shows an anomalous expansion behavior. You can see in this temperature around the Ts, there is almost zero thermal expansions. And this anomalous thermal expansion behavior is consistent with this thermal contraction of the atomic structure, which we observed from the synchrotron XRD, as we showed you before. And this nanoglass also shows the enhanced creep behavior at a room temperature. The nanoglass exhibits a smaller stress exponent, more obvious creep deformation, and faster creep rate comparing to the metallic glass. And this pronounced creep plasticity of the nanoglass is attributed to its initial excess-free volume and smaller shear transformation zone volume during the deformation. And in a long period, people always think the material glass has a uniform structures. However, just in recently, and people start to realize this structure heterogeneity is intrinsic features in the material glass. And this stress realization is one of the effective methods to measure this structure heterogeneity in material glass. And here, in principle, we will know the nanoglass with the interface structure has stronger structure heterogeneities. So it results in a larger stress realization as shown in the tables. And also the realization, this dynamic realization is the inherent features in glass because glass is a metastable materials. And the beta realization is especially important because it is closely related with its mechanical properties of the material glass. And the nanoglass shows stronger beta realizations, which indicate the nanoglass may have better mechanical performance than the material glass. And the material glass is a promising material because it brings the highest stress in the metals, but it is brittle. The brittleness is the Achilles heel of the material glass for applications. So, presuming this strong but not brittle material glass is the dream of this material scientist. And after the Professor Greiter posed this nanoglass concept, and there has a lot of simulation work to demonstrate this nanoglass would show the enhanced plasticities because this interface can undertake more deformation and form these multi-shear bands to retard these catastrophic failures. And our experiments results support this simulation work. And the nanoglass shows this plasticity in both this compression and the tensile test, which is significant improvement in the mechanical properties in material glass. So here is the conclusions. And first, I would like to know the nanoglass is a new non-crystal materials with turnable atomic structures. And second, I would like to know this multi-phase pulsed electron deposition is a low-cost, high-efficiency technique to prepare these high-quality nanoglasses. And the last I would like to know is with this turnable structure of the nanoglass, the structure-dependent property could be controlled. And also, I would like to thank all these collaborators, and some are listed as this course, and some may not. And I also would like to thank this financial support from this MSFC, the DFG, and also from the Jiangsu province.